All right, folks, get ready to unlock some serious knowledge. Because today, we're diving deep, deep into the world of algorithms.
Yeah.
We've got Thomas Cormen's Algorithms Unlocked as our guide for this deep dive.
Nice.
The whole book.
Oh, wow.
Consider this your crash course
Okay.
on everything from sorting data to the limits of computation.
I like it.
Buckle up. It's going to be a fascinating ride.
I'm excited to break these concepts down. Cormen has a real knack for making this stuff accessible, even if you don't have a computer science degree.
Absolutely.
Yeah.
Speaking of accessible, Chapter 1 jumps right in with, what are algorithms and why should you care?
Right.
It's like he's anticipating the eye rolls from anyone who thinks algorithms are just for tech wizards.
And rightfully so. The truth is, algorithms are running behind the scenes of so much of our daily lives.
Yeah.
Like, consider how streaming services suggest what to watch next based on your viewing history.
Yeah.
That's an algorithm at work.
Yeah, it's like having a personal DJ for your movies and shows.
Exactly.
Yeah, and what about online shopping? Those, you might also like recommendations, are definitely not a coincidence.
Exactly. Those suggestions are powered by algorithms that analyze your browsing and purchasing patterns to predict what you might be interested in. It's all about using data to make informed decisions.
Yeah.
Which is essentially what algorithms do best.
So they're like superpowered decision makers, but instead of emotions, they use pure logic and data.
Right.
That makes sense.
Yeah.
But how does this translate into those more technical examples we hear about, like sorting and searching?
Well, let's take searching.
Okay.
Imagine you need to find a specific file on your computer. You could go through every single file one by one.
Oh, yeah.
But that would take forever.
Yeah.
That's where algorithms like binary search come in.
Okay.
If your files are sorted alphabetically, binary search can quickly zero in on the file you're looking for by repeatedly dividing the search space in half.
So it's like playing that guess the number game.
Exactly.
Where you keep halving the range until you hit the target.
Yeah.
Efficient and way faster than checking every single file.
Exactly. And that's just one example of how algorithms can make complex tasks more manageable.
Yeah.
Cormen does a great job in Chapter 2, How to Describe and Evaluate Computer Algorithms.
Yeah.
Of breaking down how we represent these problem-solving steps in a way computers understand.
Okay, so we're talking about translating human logic into computer language.
Yeah.
Is that where pseudocode comes in?
You got it. Pseudocode is like a simplified programming language.
Okay.
It's not actual code that a computer can execute, but it helps us outline the steps of an algorithm.
Yeah.
In a way that's both human readable and easily translated into a real programming language.
So it's like creating a recipe.
Yeah.
For the computer to follow. But recipes can be simple or super complex.
Right.
How do we measure how efficient an algorithm is?
That's where big O notation comes in.
Right.
It's a way to describe how the performance of an algorithm scales as the input size grows.
Okay.
It's not about precise measurements, but about understanding the overall trend. For example, an algorithm with a time complexity of O means its execution time increases linearly with the input size.
Okay.
Double the input, double the time.
So it's like a speedometer for algorithms, telling you how fast they'll go as the data piles up.
Yeah.
Makes sense. Now let's talk about the actual tasks these algorithms perform. Chapter 3 dives into algorithms for sorting and searching.
Yeah.
Which sounds pretty self-explanatory, but what's the big deal about sorting? Why is it so crucial in computer science?
Think of it this way. Imagine trying to find a book in a library where the books are randomly placed on the shelves.
Yeah.
It would be a nightmare.
Yeah.
Sorting is about organizing data in a way that makes it easy to search, retrieve, and analyze. It's a fundamental operation.
Okay.
That underpins countless other tasks.
So sorting is like bringing order to the chaos of data.
Yeah.
It's the Marie Kondo of the digital world.
I like that.
And I bet there are tons of different ways to sort things, right?
Absolutely. Cormen covers several sorting algorithms, each with its own strengths and weaknesses.
Okay.
We've got selection sort, where you repeatedly find the smallest element and swap it to the front.
Okay.
It's straightforward, but can be slow for large data sets. Then there's insertion sort, which is like sorting a hand of cards. You start with an empty hand and gradually insert cards into their correct position.
Sounds like a more hands-on approach, but probably not the most efficient for a computer dealing with massive amounts of data.
You're right. That's where more sophisticated algorithms like merge sort come in.
Okay.
It's a divide and conquer strategy. You split the data in half, sort each half recursively, and then merge the sorted halves together.
Divide and conquer, a classic strategy. It's like breaking down a complex problem into smaller, more manageable chunks. And what about quicksort? I've heard that one's pretty popular.
Quicksort is another efficient algorithm that relies on picking a pivot element and partitioning the data around it. Everything smaller than the pivot goes to one side, everything larger to the other. Then you recursively sort the two partitions. It's known for its speed, especially for larger data sets.
So many sorting options. It's like a buffet of algorithms, each with its own flavor profile. And I bet the choice of which one to use depends on the specific data and the task at hand.
You're absolutely right. There's no one-size-fits-all solution when it comes to sorting.
Yeah.
It's about understanding the trade-offs, the efficiency, and the best fit for the problem you're trying to solve.
And speaking of finding the best solution, Chapter 4 throws down a challenge with a lower bound for sorting and how to beat it. What's this lower bound all about?
It refers to a theoretical limit on how fast comparison-based sorting algorithms can be.
Okay.
It's like a speed limit for sorting. For algorithms that rely on comparing elements, the best we can do in terms of time complexity is O(n) log n.
A speed limit for algorithms. That's fascinating. But I'm guessing there are ways to break these limits, right? Like those speedsters who find creative ways to bypass traffic.
You got it. There are situations where we can beat this lower bound by exploiting specific properties of the data.
Okay.
For example, if you're dealing with integers within a limited range, you can use counting sort, which doesn't rely on comparisons at all.
Oh, interesting.
It simply counts the occurrences of each element and then constructs the sorted output based on those counts.
It's like cheating at the sorting game by using a completely different set of rules. I love how algorithms push the boundaries of what's possible.
And just when you think you've grasped the basics, Cormen introduces a new character in Chapter 5, the directed acyclic graph,
Right.
or DAG for short.
DAGs. They sound a bit intimidating, like something out of a sci-fi movie.
They might sound complex, but they're actually quite intuitive. Imagine a flowchart where each step represents a task, and the arrows indicate dependencies between tasks. That's essentially a DAG. It's a way to visualize relationships where there's a clear direction, a flow from one step to the next.
Okay, so DAGs are like flowcharts for complex processes. Cormen actually uses the example of getting dressed in the morning to illustrate DAGs, right?
He does.
Okay.
It's a surprisingly relatable example. Think about the order in which you put on your clothes.
Right.
You can't put on your shoes before your socks.
Right.
And you can't put on your jacket before your shirt.
Right.
Those dependencies create a DAG showing the logical order in which the tasks must be completed.
I never thought I'd analyze my morning routine in terms of directed acyclic graphs, but it makes sense. And I bet these DAGs have applications beyond just getting dressed.
Absolutely. They're used in all sorts of real-world scenarios, like project management,
Yeah.
where they can help visualize the critical path of a project, identifying tasks that must be completed in a specific order to avoid delays.
So DAGs are like a project manager's secret weapon,
Yeah.
helping them map out complex workflows and optimize efficiency. Speaking of optimization, Chapter 6 takes us on a quest for the shortest paths. I'm assuming this goes beyond just finding the fastest route on Google Maps.
You're right. While finding the shortest path between 2 points on a map is a classic example, the concept of shortest paths applies to any kind of network, be it a road system, a social network, or even a financial market.
So it's about finding the most efficient way to navigate any interconnected system. What are some of the key algorithms for finding shortest paths?
One of the most famous is Dijkstra's algorithm.
Right.
It's a classic method for finding the shortest path between two nodes in a graph where all the edges have non-negative weights. Imagine a network of roads where the weights represent distances.
Yeah.
Dijkstra's algorithm systematically explores the network, finding the shortest path from a starting node to all other nodes.
Sounds like a powerful tool for optimizing logistics and transportation networks.
Exactly.
Yeah.
And then there's the Bellman-Ford algorithm, which can handle scenarios where some edges have negative weights. Think about financial markets, where sometimes there are opportunities for arbitrage,
Yeah.
where you can actually gain value by going through a cycle. Bellman-Ford can detect these situations, which Dijkstra's algorithm can't.
So it's like Dijkstra's algorithm with a built-in radar for detecting financial opportunities.
Yeah.
Pretty impressive.
Yeah.
Now let's switch gears and dive into the world of text manipulation. Chapter 7 is all about algorithms on strings. It's time to unleash our inner wordsmiths.
Get ready to untangle the complexities of strings. This chapter explores how we can analyze, manipulate, and extract meaning from textual data.
Okay.
Think about how search engines can instantly find relevant documents among billions of web pages.
Yeah.
That's the power of string algorithms at work.
So we're talking about the algorithms behind everything from spell checkers to DNA analysis. Right?
Exactly. Cormen covers a range of string algorithms, from simple pattern matching to more complex operations like finding the longest common subsequence between two strings.
Okay.
This is used in genetics to compare DNA sequences and identify similarities.
It's like finding the shared ancestry between two strands of digital DNA.
Yeah.
Fascinating. What other string slinging techniques does Cormen cover?
One intriguing concept is edit distance,
Okay.
a way to measure how similar or different two strings are.
Right.
It quantifies the number of edits, insertions, deletions, substitutions required to transform one string into another. Think about spell checkers.
Yeah.
They use edit distance to suggest corrections for misspelled words.
So it's like a digital measuring tape for words.
Right.
And then there are those finite automata we talked about earlier.
Yeah.
Those seem to play a big role in string manipulation as well.
They do. Finite automata are essentially pattern matching machines.
Okay.
They can scan through text at lightning speed, identifying specific sequences of characters.
Like digital detectives searching for clues hidden within a sea of words.
Exactly.
I love it.
And with that sense of digital intrigue, we find ourselves at the doorstep of Chapter 8, Foundations of Cryptography. Get ready to enter the world of secret codes and digital espionage.
Oh, I'm already feeling like a secret agent. Cryptography has always seemed mysterious and complex. Is Cormen able to demystify it for us non-experts?
He does a fantastic job of breaking down the fundamental concepts. Cryptography is essentially about protecting information,
Right.
ensuring its confidentiality and integrity. We're talking about techniques for encrypting data, making it unreadable to anyone without the proper decryption key.
So it's like creating a digital lockbox that only authorized users can open.
Yeah.
What are some of the key encryption methods Cormen covers?
He starts with the basics,
Okay.
explaining concepts like symmetric key cryptography,
Yeah.
where the same key is used for both encryption and decryption. Then he delves into more sophisticated techniques like public key cryptography, which uses a pair of keys, a public key for encryption, and a private key for decryption.
Public key cryptography, that's the one that revolutionized online security, right?
Yeah.
The idea that you can share your public key with anyone and they can use it to send you encrypted messages that only you, with your private key, can decrypt.
Right.
It's like having a digital mailbox with a special lock that only you have the key to.
That's a great analogy.
Yeah.
Public key cryptography is the foundation of secure online communication, enabling everything from secure online shopping to confidential email exchanges.
It's amazing how these seemingly abstract mathematical concepts have such a profound impact on our digital lives. Speaking of profound impact, Chapter 9 takes us into the world of data compression. Get ready to squeeze those bits and bytes.
This chapter is all about efficiency.
Okay.
Finding clever ways to represent data using fewer bits without losing any essential information. Think about streaming movies or downloading large files.
Right.
Data compression makes these processes much faster and more efficient.
So it's like packing a suitcase for a trip. You want to fit in as much as possible without wasting space.
Exactly.
Right.
And Cormen covers some fascinating compression algorithms like Huffman coding, which assigns shorter codes to more frequently occurring characters. It's like creating a shorthand language for data, making it more compact.
So it's all about finding those patterns, those repeating elements, and representing them in a more efficient way.
Precisely.
Yeah.
And then there's LZW compression, which builds a dictionary of common patterns and replaces those patterns with shorter codes.
Okay.
This is how GIF and TIFF images are compressed.
It's like creating a secret code book for commonly used phrases, making the communication more concise. Data compression. It's a testament to human ingenuity.
Right.
Finding ways to optimize the way we store and transmit information.
Yeah.
And just when you think you've reached peak optimization, Cormen throws down the gauntlet with Chapter 10, Hard Problems. Get ready to face the ultimate algorithmic challenge. Hard Problems. It sounds a bit ominous. Are we talking about problems that are impossible to solve?
Not necessarily impossible, but certainly challenging.
Okay.
This chapter explores the realm of NP-complete problems.
Yeah.
Problems that seem to defy efficient solutions.
NP-complete problems. Those are the ones that keep computer scientists up at night, right?
They do.
Okay.
The defining characteristic of NP-complete problems is that the time it takes to find the optimal solution grows exponentially as the input size increases.
Oh, wow.
It's like trying to find a needle in an ever-expanding haystack.
Sounds like a recipe for algorithmic frustration.
Yeah.
What are some examples of these NP-complete brainbusters?
One classic example is the traveling salesperson problem.
Okay.
Imagine you're a salesperson who needs to visit a set of cities and return to the starting point.
Right.
The challenge is to find the shortest possible route. Seems straightforward, right?
Yeah.
But as the number of cities increases, the number of possible routes explodes exponentially.
So it's like a choose-your-own-adventure book with millions of possible endings.
Yeah.
And you have to find the shortest path through all those choices.
Exactly.
Yeah.
And another notorious NP-complete problem is the knapsack problem. You have a knapsack with a limited weight capacity.
Okay.
And you need to choose which items to pack to maximize the total value while staying within the weight limit.
Okay, that one's relatable. It's like packing for a trip, but with a mathematical twist.
Yeah.
So what's the deal with these NP-complete problems? Can we solve them efficiently, or are we doomed to eternal algorithmic struggle?
That's the million-dollar question. We haven't yet proven that they're impossible to solve efficiently, but no one has found a way to do it yet.
Right.
The question of whether P equals NP,
Right.
whether every problem whose solution can be easily verified can also be easily solved,
Right.
is one of the biggest unsolved problems in computer science.
It's a question that has implications far beyond just algorithms.
Yeah.
It touches on the very nature of computation, the limits of what we can know and solve.
It does. And that, my friend, brings us to the end of part 1 of our epic deep dive into Algorithms Unlocked.
We've covered a lot of ground, from the fundamentals of sorting and searching to the mind-bending world of NP-completeness.
Right.
But fear not, dear listener, our algorithmic adventure continues in part 2.
We'll delve deeper into the concepts we've introduced today, explore the beauty of recursion, and uncover the power of dynamic programming. Stay tuned.
Absolutely.
Yeah.
Welcome back to our algorithmic odyssey through Algorithms Unlocked. Last time we left off on a cliffhanger, pondering those hard problems that seem to defy easy solutions.
Those NP-complete problems are definitely brain twisters, but they highlight a crucial aspect of algorithmic thinking. Efficiency isn't just about finding a solution, it's about finding the best solution in a reasonable amount of time.
Right, because what good is a solution if it takes longer than the age of the universe to compute?
Right.
It's like having a map that tells you the perfect route,
Yeah.
but takes years to read. Speaking of elegant solutions, let's rewind a bit and explore one of the most mind-bending yet beautiful concepts in computer science. Recursion.
Recursion, where a function elegantly calls upon itself to solve smaller, self-similar problems. It's like holding up a mirror to another mirror, creating an illusion of infinite depth.
I love that visual. But how does this mirror effect translate into solving real problems? Give us a concrete example.
Imagine you're trying to calculate the factorial of a number, say 5.
Okay.
That's 5, 4, 3, 2, 1.
Right.
A recursive approach breaks this down beautifully.
Okay.
The factorial of 5 is simply 5 times the factorial of 4.
Okay.
And the factorial of 4 is 4 times the factorial of 3, and so on. It's like a chain reaction of calculations, each one relying on the result of a smaller, similar calculation.
So it's like each step in the process is a smaller version of the original problem.
Right.
And this chain reaction keeps going until you hit what's called a base case.
Exactly. The base case is the simplest version of the problem, one that can be solved directly without further recursion. In our factorial example, the base case is the factorial of 1, which is just 1.
So it's like setting up a series of dominoes,
Right.
and the base case is the one that starts the whole chain reaction.
Yeah.
Pretty neat. Now, I've heard that recursion is closely linked to another optimization technique, dynamic programming. Is that right?
You're spot on. Dynamic programming builds upon the idea of breaking down problems into smaller subproblems, but with a clever twist.
Right.
It's all about remembering the solutions to those subproblems to avoid redundant calculations. Think of it as an algorithm with a built-in memorization superpower.
Memorization, it's like giving the algorithm a photographic memory.
Right.
So it doesn't have to resolve the same problem over and over again. Give us an example where this memory trick comes in handy.
Imagine you're planning a road trip with multiple stops. You want to find the shortest route that visits all your destinations. A brute force approach would involve calculating the distance of every single possible route, which would be computationally expensive, especially as the number of stops increases.
Yeah, that sounds like a logistical nightmare. Dynamic programming to the rescue.
Exactly. With dynamic programming, as you calculate the shortest path to each destination, you store those distances in a table.
Okay.
Then, when you need to calculate the shortest path to a later destination,